Hello everyone and welcome. My name is Jason Gregerson and this video is going to be Introduction to First Order Systems of Differential Equations. We're going to have two goals in this video. The first is to review vector-valued functions, and then next we'll look at our first order systems and express those systems in matrix vector notation. So let's get started by looking at vector-valued functions. So as a review, vector-valued functions are just functions whose outputs are vectors. So for instance, if we look at an example, let's let u of t, so this vector-valued function is a function of t, but the output will be a vector, maybe u1 of t and u2 of t. So each component of that vector output could also be a function of t. So for example, we'll let this guy be t squared and the square root of t plus 1. That's our vector valued function. And so like all functions, we could evaluate our function at some specific value. So if I input t equals 1, the output in this case would be 1 squared, which is 1, and the square root of 2. Now the other thing we like to do with functions is take derivatives. So if I want to take the derivative of this vector valued function, all I'm going to do is take the derivative of each of the components. And so in this case, I would have 2t and 1/2 the quantity t plus 1 to the negative 1/2 power. So take the derivative of a vector valued function, we take the derivative of each of its components. And so because this vector valued function is only a function of t, one variable, one independent variable, we can actually clean up the notation and just write this as the vector u prime, and its components would be u1 prime and u2 prime like that. Okay. But we could have other vector valued functions that are functions of more than one input. For instance, I could let f be a vector valued function that takes inputs t and u1 and u2. And notice that doesn't necessarily mean that these are all independent variables. I still could write this notation even if u1 and u2 were possibly functions of t. And so in this case is one example of what this vector valued function might look like. The first component might be 2u1 squared plus 4t, and the second component might be 6u2 cubed minus t squared as some sort of random example of a vector valued function of more than one input. And certainly I could evaluate this at input values as well, and I could also take the derivatives, but now I'd have to be a little more careful because if I take the derivative, we need to know with respect to what variable potentially. And so I might look at the partial of f with respect to u1, for example, in which case I'd have to treat all the other variables like they were constant. And so if I'm doing this, I'm just going to take the partial of f with respect to u1 of each of the components. So in this case, I would get 4u1 plus 0 and 0 in the second component. So in this case, I would just get 4u1, 0 as the vector. And certainly I could do the same thing with the other inputs. So I could look at that one if I want as well. All right, so let's use this notation to talk about systems of first order differential equations. All right, so a system of first order differential equations is just a set of n first order differential equations with n unknown functions. So we're going to let this vector valued function u be u1, u2, where both u1 and u2 are functions of the independent variable t. And we're going to look at these two examples of systems below. So if I look at the system on the left, I can see that if I've defined u to be u1, u2, then the left-hand side of this is just going to be my u prime. Now the right-hand side is going to be a vector function. In this case, this vector function is a function of t and u1 and u2, something like that. And that's really all I can do to simplify this. This would be the general notation for this system of first order differential equations. Now if I look at the one on the right, I might start to do the same thing. This left-hand side can still be the vector u prime. However, when I look at each one of these individual equations, because this equation is linear with respect to its dependent variables u1 and u2, and this equation is also linear, this actually is a linear system of differential equations, a linear system of differential equations. If I have a linear system, I can simplify the expression here by looking at the content that has my dependent variables, and I should be able to rewrite that as a matrix times my vector u. So in this case, I'm going to have a matrix where I pull the coefficients of those dependent variables times the vector u. And I will, in this case, have some extra t stuff left over, and so I could just wrap that into a vector-valued function of t. So I'm defining f in this case, that vector-valued function, to be the vector t squared and 1 over t. So I've really rewritten this as u prime is equal to some matrix A times the vector u plus f of t. So we've re-expressed the system of first-order differential equations in terms of this vector notation. And this will really allow us to leverage what we already know about first-order differential equations and relate that to first-order systems. For instance, this expression looks pretty similar to the general expression for a first-order differential equation, where this would just be Tx in general. And so we'll use that same notation to talk about existence and uniqueness and the general theory of first-order systems, which will be very similar to the general theory of first-order differential equations. And then over here, when we look at the linear system, well, actually, we have this matrix A, but it's not actually required to be all constants like it was in our case. In general, each of those components of the matrix could be functions of t. And when we look at this expression, it looks very similar to our first-order linear differential equation, which might look like this. And so if we relate our systems to what we already know about first-order differential equations, there's going to be a lot of similarities. And that's what we're going to look at moving forward. All right, so in this video, we've learned how we've done a review of vector-valued functions. We've looked at first-order systems, learned how to rewrite them in terms of the matrix equation. That concludes this video. Thank you very much.